Welcome back to the Comptia Networks Plus course. 5 GHz 802.11ac. 802.11ac is a Wi-Fi standard that works in the 5 GHz range and delivers up to 1 gigabit throughput that was approved by the 802.11 Standards Committee in January 2014. Still, just as it is with 802.11n, you won't find that the speeds described in the standard actually line up with the marketing material. For example, for a single link, which is basically one host to access point, the best throughput you can hope to get would be the 500 megabits per second, which is fantastic if it actually happens, but unless you have a gigabit internet connection, 802.11ac won't really help that much. To be fair, in a small network, or if you're transferring files in your internal wireless LAN or your internal network, this new specification could actually be useful. At this point, you'll probably be wondering how these people can claim to achieve these theoretical rates, right? That's an excellent question. They got these values by increasing the RF band usage from 20 MHz wide channels with 802.11a, b, g to 40 MHz with 802.11n and up to 160 MHz wide channels with 802.11ac. But again, for typical commercial 802.11ac products, 80 MHz would be a lot more realistic. The problem with this scenario centers on the fact that if any interference is found in the 80 MHz wide channel, it drops down to 40 MHz wide channels worse. If interference is still found at that level, it will drop even further down to 20 MHz wide channels. In addition to the wider channels, we can also get more drop even further down to 20 MHz wide channels. In addition to the wider channels, we can also get more multiple input, multiple output spatial streams than we can with 802.11n up to 8, where 802.11n only supported 4. Furthermore, with optionally a downlink of multi-user, multiple input, multiple MIMO support up to 4 clients, and with most important, a modulation of QAM 256 compared to QAM 64 with 802.11ag. The last thing I want to point out is the fact that 802.11n has added fields in the wireless frame to identify 802.11a and 802.11g as high throughput, whereas 802.11ac has 4 fields to identify the frames as very high throughput VHT. Comparing 802.11n standards. Before I move on to wireless installations, take a look at figure 12.6, which lists for each of the IEEE standards in use today the year of ratification as well as the frequency, number of non-overlapping channels per physical layer, technique and data rates. So I'll just go through them quickly. Ratified frequency band, number of channels, transmission data rates: 802.11n 1997 2.4 GHz, 3 IRFHSS DSSS 1 2. 802.11b 1999 2.4 GHz, 3 DSSS 1 2 5511. 802.11a 1999 5 GHz up to 23 OFDM 6 9 12 18 24 36 48 54. 802.11g 2003 2.4 GHz, 3 DSSS OFDM 1, 2, 5, 5, 11, 6, 9, 12, 18, 24, 36, 48, 54, 802.11n 2010 2.4 gigahertz, 5 gigahertz varies. DSSS CCK OFDM 100 plus. 802.11 AC 2013 5 gigahertz varies. OFDM 1000 plus. I mentioned earlier that 802.11b runs DSSS, whereas 802.11g and 802.11a both run the OFDM modulation technique. 802.11ac runs up to OFDM 256 QAM. Range comparisons. Now let's take a look at figure 12.7, which delimitates the range of comparisons of each 802.11 standard and shows these different ranges using an indoor open office environment as a factor. We'll be using default power settings. You can see that to get the full 54 megabits per second benefit of both 802.11a and 802.11g, you need between 50 feet and 100 feet maximum away, which will likely be even less if there happen to be any obstructions between the client and the access point. 802.11n gives more distance than all three standards shown in the figure, up to twice the distance, and understand that 802.11ac just won't give you more distance in 802.11n. Wireless network components. Though it might not seem this way to you right now, wireless networks are less complex than their wired cousins because they require fewer components. To make a wireless network work properly, all you really need are two main devices: a wireless access point and a wireless network interface card, the latter of which is typically built into your laptop. This also makes it a lot easier to install a wireless network because basically you just need an understanding of these two components in order to do so. Wireless access points. You'll find a central component like a hub or switch in the vast majority of wired networks that serves to connect hosts together and allow them to communicate with each other. It's the same idea with wireless networks. They also have a component that connects all wireless devices together, only that device is known as a wireless access point, WAP, or just access point. Wireless access points have at least one antenna, typically two for better reception, a solution called diversity, and up to 8 to support 802.11ac and an Ethernet port to connect them to a wired network. Figure 12.8 shows an example of a typical wireless access point. You can think of an access point as a bridge between the wireless clients and the wired network. In fact, an access point can be used as a wireless bridge depending on the settings to bridge two wired network segments together. In addition to the standalone access point, there is another type of access point that includes a built-in router, which you can use to connect both wired and wireless access points to the internet. The most popular home brand being Linksys, a division of Cisco. In summation, an access point can operate as a repeater, bridge, switch, or router, depending on its hardware and implementation. These devices are usually known as surprise wireless routers. They're usually employed as network address translation. NAT serves by using one ISP provides a global IP address to multiplex numerous local IP addresses that are generally doled out to inside clients by the wireless router from a pool within the 192.168.x.x range. Wireless network interface card. Every host that wants to connect to a wireless network needs a wireless network interface card, NIC, to do so. Basically, a wireless network interface card does the same job as a traditional network interface card, but instead of having a socket to plug a cable into, the wireless network card has a radio antenna. In addition to the different types of wireless networking, I'll talk about those in a minute. Wireless network interface cards, like other NICs, can differ in the type of connection they use to connect to the host computer. The wireless card shown in figure 12.9 is used in a desktop PC. There are various options for laptops as well. All new laptops have wireless cards built into the motherboard. Wireless antennas. Wireless antennas act as both transmitters and receivers. There are two broad classes of antennas on the market today: omnidirectional or point to multipoint, or directional or Yagi point to point. Yagi antennas usually provide greater range than omni antennas or equivalent gain. Why? Because Yagis focus all their power in a single direction, whereas omnis must disperse the same amount of power in all directions at the same time. A downside to using a directional antenna is that you've got to be much more precise when aligning communication points. This is why a Yagi is really only a good point for point-to-point bridging of access points. It's also why most access points use omnis, because often clients and other access points could be located in any direction at any given moment. To get a picture of this, think of an antenna on your car. Yes, it's non-networking example, but it's still a good one because it clarifies the fact that your car's particular orientation doesn't affect the signal reception of whatever radio station you happen to be listening to. Well, most of the time anyway. If you're in the boonies and you're out of range, something that also applies to the networking version of omnis. The television aerials that some of us use are old enough to remember rotating into a specific direction for certain channels of examples of Yagi antennas. How many of you labelled your set-top antenna to dial for the actual TV stations you could receive? Believe it or not, they still look like the same to this day. Both omnis and Yagis are rated according to the signal gain with respect to an actual or theoretical laboratory reference antenna. These ratings are relative indicators of the corresponding production antenna's range. Range is also affected by the bit rate of the underlying technology, with higher bit rates extending shorter distances. Remember, a Yagi will always have a longer range than equivalent rated omni, but as I said, the straight line Yagi will be very limited in its coverage area. Both antennas are also rated in units of decibel isotropic or decibel dipole dBd based on the type of reference antenna. Isotropic or dipole or equivalent frequency that was initially used to rate the production antenna. A positive value for either unit of measure represents a gain in signal strength with respect to the reference antenna. Merriam-Webster defines isotropic as exhibiting properties as velocity of light transmission with the same values when measured along axis in all directions. Isotropic antennas are not able to be produced in reality, but their properties can be engineered from antenna theory for reference purposes. As a practical example, I'm going to use the Cisco system series of Aeronet access point indoor and bridge outdoor antennas. Table 12.3 describes the effect that gain ratings and attempted bit rates have on range limitations. So I'll leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.